All right, so we're moving on to the next section. This is 2.6, I believe, and now we're going to start talking about those rational functions. You guys might remember those for the ones for having our vertical and horizontal asymptotes. You get kind of those weird curving graphs that kind of went in opposite directions a lot. Anyway, so we're going to talk about the domain of those and how to find the horizontal and vertical asymptotes again. So just to define a rational function, remember your key word in there is ratio, which means they can be written as a fraction. So rational numbers can be written as a fraction. Rational functions can be written as a fraction of two polynomial functions. So n and d are both polynomials, and they're in a fraction. Okay, so the domain is of f of x of this function is all x such that the denominator does not equal 0. Because remember, if the bottom equals 0, we're dividing by 0. That's not allowed in math. So that's where we're going to have some domain restrictions. And a lot of time that's going to be our vertical asymptote. The zeros of our function are all x values that make the numerator 0. Right? Because if the top is 0, 0 divided by, it doesn't matter, anything in the bottom, 0 divided by anything will make our whole polynomial function 0. So that's how we're going to find the x-intercepts as well. Remember that those mean the same thing as the x-intercepts. All right, so let's take a look. Our first one says find the domain and zeros of this function. So to find the domain, we want to know when does the denominator, x squared minus 4, equal 0. We can even say that the denominator cannot equal 0. And if you add 4 over, x squared cannot equal 4. And if we take the square root, we get x cannot equal positive or negative 2. So my domain is all x values such that x cannot equal positive or negative 2. And if we write that in that interval notation, so my domain would go from negative infinity to negative 2, non-inclusive because it can't equal that value. Then we can go from negative 2 up to positive 2, non-inclusive. And then we can go from positive 2 to infinity. So unfortunately, when you write it this way, it's a big, long, ugly way of writing the domain. Otherwise, you can just say it's all real numbers as long as x does not equal positive or negative 2. All right, next, finding the zeros of our function, we want to know when is the numerator equal 0. So to find our zeros, we're going to take 2x plus 1 and find its zeros, setting it equal to 0. So subtract 1, 2x equals negative 1, and divide by 2. Okay, so we have a 0 of negative 1/2, which means my x-intercept would be negative 1/2, comma 0. Okay, so there's our first example. Let's take a look at our next one. Now we've got some notes that are going to talk about when these occur and how to come up with their values. Okay, so the line x equals a, that's a vertical line, is a vertical asymptote if our function is going towards positive infinity, if it's shooting up super fast, or if it's going towards negative infinity at that value. So that'll make more sense when we graph those, but my graph will either be shooting up towards positive infinity, that's what this is saying, or shooting down towards negative infinity, which is what this is saying, as we get closer and closer to that value of a. And this is typically those values in the denominator that give us division by 0. Okay, the line y equals b, so this is a horizontal line, y equals, is a horizontal asymptote if my function is shooting off towards positive or negative infinity left or right as my y values get closer and closer to b. And this will make some more sense when we're graphing it. Okay, so vertical asymptotes occur when our numerator is equal to 0. So if my denominator is equal to 0. So anything that gives us division by 0, typically that will be a vertical asymptote. Very rarely will that not be true, and that's really only if you can simplify the top and bottom and cancel out some common factors. You guys might remember those were holes in the graph, just a singular hole. So for instance, your curve might go something like this, and then there'd be a singular hole and it'd continue. But that's only if they have a common factor. Instead of that 0 being a vertical asymptote, it's a hole in the graph. Anyway, the horizontal asymptotes depend on the degrees of the top and bottom. So we're going to look at the degree of the polynomial on top and the degree of the one on bottom. Okay. If they're equal, so if the degree of n and d is the same, our horizontal asymptote is equal to the ratio of the leading coefficients. So for instance, if we have, say, 2x over 3x, my degrees here are the same, x to the first and x to the first. And if that's true, we just do the ratio of their leading coefficients. So y equals 2/3 would be where my horizontal asymptote would be for that graph. Okay. If n is less than d, so d has the higher degree, maybe you have like 3 on top and 5x on bottom. So the degree of the top is actually x to the 0 power, and the bottom is x to the first, so the top is less than the bottom. In this case, for me, I find it easy to think of the top as I have 0 x to the firsts, and then you do kind of what we did above. Pretend that the degrees are the same, and 0 divided by 5, those leading coefficients, gives you 0. And that's why it will always be, if this is true, it's always y equals 0. The x-axis plays our horizontal asymptote. It's a plus. However, if the degree of the top is larger than the bottom, so when it's top-heavy by degree, basically it's no longer a horizontal asymptote. It could be a slant asymptote, which is like a diagonal line it curves towards, or it can be some other function. You can actually have like a parabola is like what your graph curves towards infinitely forever. They look pretty weird. And if you want to come up with that equation of the non-horizontal asymptote, which I don't think we have to do yet at least, you can find that by doing polynomial long division. So you actually do the division, and the quotient tells you what your non-horizontal asymptote would be. So you don't need the remainder, you can just kind of cut off or lose the remainder, but the quotient of the long division gives you that equation. All right, well, let's put some of this in practice. All right, so it wants me to graph this with a calculator. Okay, so I've already typed this in, and I'll give you guys a tip when you go to type these in your calculator. Now you can see it's auto-formatted pretty nicely for me there, but the easiest way to type these in, and I'll redo this one, is, for me, put everything in the top in parentheses, 2x minus 5, and then divided by everything in the bottom in parentheses. And now we don't have to mess with the fraction template. I don't know, sometimes that messes students up. But anyway, here's our graph, 2x minus 5 over x minus 2. So we've graphed that with our graphing calculator. Now it says find the domain. Find the zeros, horizontal asymptotes, and domain. Okay, well, we can do some of this by hand. So to find the zeros, we take the numerator, 2x minus 5, and set it equal to 0. So we can add 5. So we can add 5 to both sides. 2x equals 5, and divide by 2. We get 5 halves, or 2.5. Okay, so there's my zeros. To find my horizontal asymptote, we'll come back to that. Let's do the vertical asymptote. Typically that's easier. The vertical asymptote is the one that gives us division by 0. So my vertical asymptote, what's going on with my pen here? My vertical asymptote is x minus 2 equals 0. Add 2 over, and my vertical asymptote is the line x equals 2. To find my horizontal asymptote, we're going to compare the degrees of the top and bottom. So the top is x to the first, the bottom is x to the first, so they are the same degree. So if we go back and look at those notes a second, when they're the same degree, It's the ratio of the leading coefficients. So when they're the same degree, we can look at that ratio of the leading coefficients. In this case, we have 2 over 1, or y equals 2 over 1, or 2. Okay, so we have a vertical asymptote at 2, a horizontal asymptote at 2. Should cross the x-axis at 5/2, or 2.5. And lastly, my domain is everything that's basically not 2. So we can write our domain from negative infinity to 2, non-inclusive, and then from 2 to positive infinity. And so let's take a look at that graph really fast. Yep, I can see at about positive 2 there looks like a vertical asymptote that my graph is curving towards positive infinity or negative infinity at. And my horizontal asymptote here is about at y equals positive 2. And I can look at a table of values. So if I go to Menu, Table, Split Screen Table, I can see some things like, hey, my y's are undefined when x is 2. That's my vertical asymptote. And as I start going out further and further in these directions, you can see that my x's, as x keeps getting bigger and bigger, my y's just keep getting closer and closer to 2. When I go the other direction, really large negative numbers, like I shoot way out to the left, I hit closer and closer to 2, but from above. And so that tells me kind of where my horizontal asymptote was. All right. Next, find the horizontal and vertical asymptotes, then just look at it and graph with a calculator. We can kind of check it with that table or a graph. Okay, so let's do the vertical asymptotes. I like to do those ones first. That's what gives me division by 0. So when is the bottom equal to 0? So x squared minus 1 cannot equal 0. That's where we're going to have vertical asymptotes. Add 1 over and take the square root. X cannot equal positive or negative 1. So we're actually going to have 2 vertical asymptotes at positive and negative 1. For my horizontal asymptote, we're going to look at the degree of the top and bottom. So the top is degree 1, the bottom is degree 2. So in this case, we're bottom heavy. When it's bottom heavy, it's going to end up being y equals 0. For the same reason I said earlier, you can think of the top as having 0 x squareds. And if we did the ratio of the matching leading coefficients, 0 over 1 would be 0. So my horizontal asymptote is y equals 0. The x-axis is going to be my horizontal asymptote. I do have a 0 of negative 1 if you set the top equal to 0, so it should cross through the x-axis at negative 1. Actually, I don't think that is going to work. In fact, it's not a 0. And in fact, I almost forgot. If I looked at the bottom here, we have a difference of squares. X, plus 1 and x minus 1. In the top, we can actually cancel the x plus 1's, and I end up with the simplified function 1 over x minus 1. So actually, a lot of this other stuff is going to change. I do have a vertical asymptote, but only at positive 1, the 0 of this. So actually, my vertical asymptote is only at x equals positive 1. And in fact, what I was saying earlier, that negative 1, the other one we would have found, the 0 of this common factor is actually just a singular hole in the graph. My vertical asymptote remains the same. The degree of the top here of 0 is still larger than the bottom, degree 1, so still y equals 0. So let's take a look at that with the calculator. We'll see that it is actually very different. So I can look at my table. Oh, this is the wrong graph. There we go. It's number 3. So here's my graph. And we thought we were going to have an x-intercept of 1, but I can tell it doesn't actually pass through there. And if I look at my table, at positive 1, even though it looks like when x is 1, well, that's where our vertical asymptote is. Sorry, at x equals negative 1. Let's take a look. So at negative 1, it looks like there's a point on my graph. But in actuality, when I look at my table, it's undefined. And that's that hole or singular hole in the graph. And so they should really have like a little circle kind kind of showing a hole there, but our graphing calculators don't do that. All right, let's do these other two a little bit quicker. So to find my vertical asymptote, set the bottom equal to 0. 4x minus 6, whenever this equals 0, this will give me my vertical asymptote. Add 6 over, and divide by 4. And we get 6/4 or 3/2. So at x equals 3/2 or 1.5, that's my vertical asymptote. For my horizontal asymptote, we're going to look at the degree of the top and bottom, and they are the same. And remember, when they're the same, we do the ratio of the leading coefficients. And this time there wasn't anything to factor out or cancel. So my leading coefficients are 2 over 4 or 1/2. So y equals 1/2, we should have our horizontal asymptote. Let's take a quick look. So here's our graph, and yep, our vertical asymptote's right about there at 3/2, 1.5, and our horizontal one is at about 1/2. That's what it gets closer and closer to. And again, you can confirm that looking at the table. Okay, our last one, vertical asymptote. So what's going to make the bottom equal 0? So when does x plus 1 equal 0? Subtracting 1, we know that's when x is -1. So there's my vertical asymptote. And my horizontal asymptote, if I look at the degree of the top compared to the degree of the bottom, this one's top heavy. And top heavy by degree means there's no horizontal asymptote. So this is some other asymptote. And in fact, if we look at the graph, because the degree difference between the top and bottom is 1, I know that my quotient is going to have to be x to the first power. And so it ends up being an equation of a line my graph curves towards. And if you do the polynomial long division, you can come up with that exact equation of the line your graph curves towards forever. All right, lots of notes today. We got 2 more examples. I think this is it. So we're asked to find the domain, horizontal and vertical asymptotes, the zeros, graph and check it with our calculator, and find a table of values. And we can do that with the calculator or just plug in some x's and y's. All right, so for my example, let's see. First, my domain. Whenever the bottom is 0, that's going to give me my vertical asymptote and my domain restriction. So when I set this thing equal to 0, we're going to take the cube root of both sides. And we end up, of course, thinking about our multiplicity. We really get 2 3 times. So because its multiplicity is 3, it will still pass through the graph. Or, sorry, this is not a 0. But it just ends up being positive 2. Sorry. That also gives me my vertical asymptote and my domain restriction. So for my domain, I can go from -infinity to 2, and from 2 to +infinity. For my horizontal asymptote, we look at the degree difference between the top and bottom. And remember, if you actually were to FOIL this out, this would be x minus 2 times x minus 2 times x minus 2. In which case, multiplying all those x's, I get 1x to the third. So the bottom is x to the third. It's a third degree. And the top is a 0 degree. And so when the bottom is larger than the top, y equals 0. And again, you can kind of think of this as there being 0 x cubes, and comparing that to the 1 x cubed in the bottom. The ratio of those coefficients, 0 divided by 1 is 0. All right, so then we're asked to graph this. And the best way to do that, if you're doing it by hand, is you would draw on your axes, plot a dotted line where your horizontal asymptote would be, and that's actually the x-axis this time, and draw in a dotted line where my vertical asymptote would be. Okay, I'm not going to try to graph by hand with this thing because it's not very good. So instead, let's look at their graph. And if I went to +2 and drew in a dotted vertical line to give myself a boundary to curve my graph towards, and a dotted horizontal line where the x-axis is, all we would do is, where my vertical asymptote is with our table, so if you're making a table, you'd put where your vertical asymptote is when x is 2, my graph is undefined, And you'd pick a couple values to the left and to the right. Generally, maybe not right up against it. You could do 1, but I might even do like 0 and -2, and maybe like 4 and 6. It should give me a good idea what's going on with this graph. So you can plug in those values. I'm going to shortcut this to try to make this a little shorter. Here's a table. If you plugged in 3, you get 3, and you plug in 4, you get, I don't know what that is, something like an 1/8 or 3/8. I think that's 3/8. Anyway, but you can plot some of those values to get our graph. It should look roughly like this. Okay, let's go over what I think is our last example here. Again, to find my domain, I can also use that to find where I have asymptotes at. So I need to know when this bottom equals 0. Unfortunately, there are no factors of 9 that add up to 1, so this is not a factorable quadratic, which means we got to resort to something more like quadratic formula. So x is equal to opposite of b, which would be -1, plus or minus the square root of b squared, so 1 squared, minus 4 times a, which is 1, times c, which is 9, all over 2 times a. So I get -1 plus or minus 1 squared is 1. -4 times 1 is -4, times 9 is -36. And I'll go ahead and multiply the bottom. 2 times 1 is 2. So I get -1 plus or minus the square root of -35 all over 2. And I don't believe that actually simplifies because my only factors are 7 and 5, other than pulling an I out for that negative sign. So it's I root 35 all over 2. So this is what x cannot equal because we would have division by 0. Now the only values x can't equal are imaginary. So my domain is actually just all real numbers. The only excluded values were imaginary, so all real numbers are still okay. There's no domain restriction. So that also means that there's no vertical asymptote, because we didn't get a real value. So no real value of x will make the denominator 0. To find my horizontal asymptote, again, we compare the degree of the top and bottom. Since they're both degree 2, I look at the ratio of my coefficients, 3 over 1, which is y equals 3. So we should have a horizontal asymptote at y equals 3. Let's take a look at our graph. And you can see this guy doesn't have a vertical asymptote, but right about where y equals 3, if you were to draw on that horizontal line, my graph will just get closer and closer. It's a pretty weird looking graph, to be honest. And so you can graph that. Obviously check with your calculator, make a table of values. Typically when we draw those by hand, when you're drawing in, so this is just in general. So if this is your x and y axis and you've plotted in, say, a horizontal asymptote maybe somewhere over here, vertical asymptote, and some sort of horizontal asymptote here, you just want to pick some x values on either side to figure out if the graph is kind of in the top or in the bottom, and usually how close it's bounded by those asymptotes. So sometimes you get graphs like that. We did these last year, so you can review notes from last year or look up some additional videos to help you out. All right, good luck.